types of questions that we are going to be answering. They're called optimization. We're going to be finding things like, use this for this. If you want to manufacture a can that would minimize your cost, you know what kind of volume you need, but you want to have the least amount of money involved in making that can as possible. If you want to maximize the acceleration of a spaceship, if medical application, what's the radius of a contracted windpipe that expels air most rapidly during a cough? Or what angle should blood vessels branch so as to minimize energy expended by the heart in pumping blood? This is kind of one of those reasons that calculus is required for so many different majors, because it has lots of applications, especially in this scenario where we are talking about maximizing and minimizing things. We have looked at some of those already, talking about we had the cost problems, we talked about revenue. So if you think about some scenarios, you would want to maximize your revenue while minimizing your cost if you were going to make something, right? You want to have as little money in it as possible, but you want to make the most that you can. So a lot of different scenarios where we look at this. We're talking about absolute maxes and mins here. An absolute max just means it is the highest point on the entire graph. Absolute min is the lowest point on the entire graph. So when I talk about absolute, that is the actual on the entire graph, the highest or lowest. Okay, not just one particular area of the graph, but the entire thing. These are sometimes called global maxes or mins. So this particular graph, we can see f of 3 equals 5. So when x was 3, the y is 5. That is the absolute max on the graph, assuming that these 2 points are endpoints and they don't keep going. Our absolute min would be f of 6 equals 2. Like I have here, you could call those global. When I talk about maximum and minimum, those are sometimes just called extreme values. So if I say find the extreme values, I want the maximums and the minimums on your graph. When you're talking about absolute or global, these can be endpoints. In contrast to absolute, we can also look at local maxes and mins. When you're talking about local, it's not the highest or lowest on the entire graph, it's just higher or lower than the points immediately surrounding it. Okay, in this scenario, you can have multiple maxes and mins. So for instance, this particular graph. This point right here, that is the lowest point on my entire graph. So that would be called an absolute min. It's the lowest point my graph ever achieves. This point right here, it is not the highest on my entire graph. But can we agree it's higher than the points on either side of it? Yeah. So this is a local max. And this point right here, it is the actual highest on my graph. So that means it's an absolute max. But it can also be a local max. This one is both. absolute maximums and minimums include the endpoints and the locals do not. So this one, even though it's the lowest, to be a local, it has to have points on both sides of it. Since there's nothing to the left, it can't be local. This one, it's the highest, so it's absolute. There are points on both sides, so it also qualifies as a local. This one right here, is it an absolute max? No. Can it be a local? No, because it doesn't have points on both sides, so that one's nothing. What would these points be right here? Local min. So, local maxes and mins can't be endpoints. But absolutes can. I have another graph on that slide. You can see this one has a local min here and here, local max here. This can't qualify as local max because there's not points on both sides. Okay. So let's start looking at some problems then. What are the maximum and minimum values of f of x equals x squared? Identify them as local or global. Global is the same as absolute. So what's x squared look like? Parabola. Okay, that is a really sad parabola, but pretend it's a little better than that. What does this one have on it? It has a minimum. Is it local, absolute, or both? Both. So local and global or absolute, whatever term you want to call it, min at f of 0 equals 0, when x is 0 and y is 0. Okay, so far so good. B, maximum and minimum values of x cubed. So what's x cubed look like? Chair. So what does that have? Nothing. Let's look at a graph. I apologize, this graph is really hard to see on here. Find a better way to put this graph on. I tried to copy it out of a book, but it did not work. Okay, if we look at this one. Absolute max. So we can agree this is the actual highest point on my graph. So that's f of 4 equals 3. When x is 4, the y is 3. Okay. Absolute min. So the lowest point on my entire graph. The lowest point that I see is right here. But what's wrong with that? It's an open. Can you give me the closest point to that open circle? No, because I can just always add another decimal point and get closer, right? If it's an open circle, you have to tell me none. There is no actual lowest point because it ends at an open circle. Okay, local max. So higher than the surrounding points. So if I look right here, this is higher than the points surrounding, but it's open, so does that count? No. This one right here. It's not connected, but do I have points on both sides of it? Yes, it's a closed circle, so that counts as a local max. So my local max, f of 0 equals -1. Would this one be? No. What about this one? Yes. F of 4 equals 3. It's local and absolute there. Local min. So lower than the surrounding points. So this one's lower, but it's open, so that doesn't count. Plus it's an endpoint, and we know local maximums can't happen at endpoints. What do you think? Can you tell me any? F of -2 equals -3. Okay. So that's a local min. Anywhere else? So, well, even though at 2, like this is lower than the points to the right of it, but the points to the left are lower than that one. Right here, this one is higher than the points on that side, so that wouldn't count. What about this point right here? Are there points on both sides of it? Yeah. Yes. Is it lower than the points on both sides of it? Yeah. So that f of -4 equals -2 is another one. Okay. So we have to watch for like the peaks in our graph. You also need to pay close attention when you have, random dots. Is it higher or lower than surrounding points? Any questions on that? Let's draw a graph here. So I want to sketch a graph that has an absolute max at 5, an absolute min at 2, local max at 3, and local min at 2 and 4. Okay, a lot of information here. So there's definitely more than one correct answer. My absolute max when x equals 5. So when x equals 5, I have to hit the highest my graph ever reaches, whatever that might be. Okay. Absolute min at 2. So when x is 2, I have to have my lowest point on the graph. Local max at 3. So I need a local. It can't be higher than this one. And I need mins at 2 and 4. Now this one is an absolute min already. If it's also a local min, that just means it can't be the endpoint. So I have to have some points to the side. And also when x is 4, I need a min. So something like this. Okay, there's my absolute min. I need a local max at 3, so we've got to come up and hit our 3. need another local min at 4, so we have to come back down, hit our 4. And I want my highest point at 5. Since it's not a local, it could be the endpoint. So something like this would work. Not the only correct answer, but one of them. What I recommend on these, once you draw it, go back through and make sure you met your requirements. You know, I have the absolute max at 5, absolute min at 2, local max 3, local min 2, local min 4. So just run back through and make sure you met your requirements. Questions there? Our extreme value theorem says if our graph is continuous, so if there's no breaks in it, if you have a closed interval, it has to have an absolute max in it. So if I'm going to start and stop somewhere without any breaks in my graph, I have to have both a highest and lowest, whether it be in the graph itself or at an endpoint. You can have more than one absolute max if you hit the same height twice. So if they're identical, you could list 2 of them there. That only works if our graph is continuous. If we had a break in it, like this open circle, this one doesn't have an absolute max. Or you might have like a vertical asymptote, and it keeps going up forever, and you don't have an absolute max. So that's only true if we know our graph is continuous. So if I wanted to find those values, these high and low points, what do you think we would do? I drew in the tangent lines. What kind of tangent lines are those? Horizontal. What's the slope of those? How do you get the slope of a tangent line? So really all we're doing is when the derivative equals 0, which is what we have done over and over again before. So that is, from Fermat's theorem, it just tells us if you have a local max or min, then the derivative is 0. Now, my question is, if the derivative is 0, does that mean it has to be a maximum or minimum? Think about x cubed. We already said it didn't have any. The derivative of this would be 3x squared. If you set that equal to 0, you get x to equal 0. This graph has a horizontal tangent line at 0, but is it a maximum or minimum? No. So just because the derivative is 0 doesn't mean it has to be a maximum or minimum. It means it could be. So we will look at when things have a derivative of 0 and then decide if it's a maximum or minimum. You also have scenarios where there might be a maximum or minimum and our derivative isn't 0. If you think about the absolute value, can we all agree that this is an absolute and a local max? Or sorry, min, not max. Okay, but the derivative is actually undefined there. When we first talked about derivatives, we talked about if it's a sharp corner, the derivative doesn't exist because there are multiple tangent lines. So we can't only look at the points where the derivative is 0, we also need to look at where the derivative might be undefined. Okay, so these points where the derivative is 0 or undefined are called critical numbers. And our maximums and minimums are going to happen at our critical numbers. So what we are going to do now is find those critical numbers. So if I gave you this function, find the critical numbers. That means find anywhere the derivative is 0 or undefined. If I want to do the derivative right now, I'd have to do product rule. What might be a little bit easier? Multiply it through first. When you multiply, you add those exponents. So you get 4x to the 3/5 minus x to the 8/5. So now we need our derivative. Exponent comes down, which gives us 12/5 x, subtract 1 from the power, minus 8/5 x to the 3/5. What do we need to do with this? Set it equal to 0. Keep in mind, a negative exponent is really just saying it's on the bottom. If I add this one over, that's like an 8x to the 3/5 over 5. So now what would we do? Cross multiply. So we get 40x, 2/5 plus 3/5 is just 1. Equals 60. Divide by 40 and you get 3/2. So the critical numbers are when x is 3/2, because that's when the derivative is 0. Is there anywhere this derivative would be undefined? Look right here. Is there any number I could not plug in for x? 0. I know right there, since x is on the bottom, it can't be 0. So 0 is also a critical number. So now we're just going to find maxes and mins. So what we will do is find our critical numbers. Then we will plug those critical numbers and the endpoints back into the original equation. Whichever one gives us the highest value is your absolute max. Whichever one gives us the lowest value is the absolute min. So we find the critical numbers, and then we're going to test them. So let's find the absolute max and min of this function on the interval -1/2 to 4. X cubed minus 3x squared plus 1, that is a polynomial, so we know it's continuous. That means there has to be critical numbers. We have a closed interval, so we should have a maximum and a minimum on this interval. So we first find our critical numbers. So we need to find when the derivative is 0. So the derivative of this would be 3x squared minus 6x. Set that equal to 0. What could you pull out of there? This is with x minus 2. So x could be, so these are the critical numbers. Is there anywhere this derivative is undefined? No, x never ended on the denominator, so this one is defined everywhere. So now, we are going to test our endpoints and these values. Our absolute maximum and minimum has to either happen at an endpoint or a critical number. So when I say test them, we are plugging them into the original. So if you put -1/2 into the original, what do we get out? You guys can find it, I'm not going to tell you. Plug it into the original, -1/2. What'd you get? 20? If you put a 0 in, I'll do that one. You get 0 minus 0 plus 1, so 1. Plug in a 2, you get 8 minus 12 plus 1, so negative 3. Plug in a 4, 64 minus 48 plus 1 gives you 17. Does everybody know where I'm getting those values? So, which one is the absolute max? Mm-hmm. 17 is the biggest y value, so that's the absolute max. Which one is the absolute min? 2. Let's look at this one. I want to know if f of x equals 2x has a maximum or minimum on the interval 0 less than or equal to x less than 1. So we need our critical numbers. What's the derivative? 2. Does that ever equal 0? No. So there are no critical points. A lot of times I'm just going to call that CP, critical points, critical numbers. Okay, so that means the only place I could have an absolute maximum in would be the endpoints. Now if you think about what this graph means, if I put in a 0, you get out 0. If x is 1, you get out 2, but 1 didn't have an equal to, so that would be an open circle. So does this graph have both an absolute max and a min? No, just a min. It has an absolute min at f of 0 equals 0. So you have to watch for open circles. Let's do okay, so our function is defined on the interval 0 to 1. Does the graph have a maximum and a minimum value? You always have the option, especially if you get something a little confusing like this, you could always graph these and figure out what it's saying. It's 1 if x equals 0, so 0, 1 is the point on my graph. It's 1 over x if x is between 0 and 1. So for instance, if I plugged in a 1, 1 over 1 is 1. If I put in 1/2, what's 1 over 1/2? 2. If I put in a 1/4, 1 over 1/4 is 4. And you can't plug in a 0. What it looks like is this. That's a vertical asymptote. So this is our graph. Could you look at that graph and tell me, does it have a maximum or a minimum? Has absolute minimum, but not an absolute max. If we wanted to do it our other way, we do our derivative. You have to do the derivative of each piece. 1 over x, that's like x to the negative 1. So its derivative is negative x to the negative 2. Or you could write that as negative 1 over x squared. What's the derivative of 1? It's 0 x equals 0. Okay. Our critical numbers are when this thing is 0 or undefined. We know it's 0 when x equals 0. Does 1 over x squared ever equal 0? No. Is it ever undefined? At where? 0. So we just get the same critical number twice. So our critical point is at x equals 0. So we just need to test our critical point and our endpoint, which was 1. If you put in a 0, our graph gives us out 1. If we put in a 1, 1 over 1 is 1. Those are the same. Looking at the graph, we know those are min. So both of these are absolute min. So we can use the graph or a combination of the graph and the function. If it's polynomials, it's very simple to do our whole derivative set it equal to 0. When it's like piecewise or something, you might need a graph to kind of back you up. We are going to stop there. The homework, tomorrow we're going to do a handout. You are actually ready for all the book problems. I'm going to take off problem 12. So the first 4 questions are just look at the picture and tell me. Absolute maximums, local maximums, and then there's some drawing pictures. Not really. All right, I'm going to be really nice. I'm going to take off 11 too because I wanted to give you a little more time in class and I haven't. So 3 through 8 and 15, I would like those done tomorrow. There's not that much